So let's start then by proving the part that I've underlined in red. So we're assuming now that we've got our function f and that we know that the first derivative at x0 exists and is equal to 0. So this is a stationary point for the function. And we're also now assuming that the second derivative at this point x0 exists and is greater than 0. And what we want to prove is that we now know that that point x0 is a local minimum of the function. So how are we going to do this? So firstly, let's call the value of that second derivative at x0. I'm going to call that p. And I'm calling it p for positive because I know that that is some real number that is strictly greater than 0, i.e. a positive real number. I've also just drawn a picture of our function here. So here is our interval ab, here is the function f here, and this is our point x0, and here the derivative of the function exists and is equal to 0, so this is the stationary point for the function. Now, so the first thing we need to do is actually think about what this truly means, because this is the information that we're starting with, that this second derivative at x0 is this positive value. So we need to now write out what that second derivative really means. So it, of course, is the derivative of the derivative. So it's the limit as h approaches 0 of the difference quotient for the first derivative evaluated at x0. So I've got here f prime, the first derivative, at x0 plus h minus the derivative at x0 divided by h. So you're going forward or backwards, depending on whether h is positive or negative, by this amount h. You're looking at what is the value of the function that you're differentiating, which is the first derivative, at x0 plus h, and then you're subtracting off what the value of the first derivative at x0 is, so your original point, so that you get a change in f prime, and then you're dividing it by the change in x, so you're getting this ratio between the change in f prime and this change in x, or change in the domain, and you're taking the limit of that ratio as you make this change in the domain smaller and smaller. Now, to help us understand what to do next, I've drawn this picture, and this is a graphical representation of, I'm putting h on the domain axis here, and then I'm thinking about plotting this function that we're taking the limit of as h approaches 0 on this codomain axis here. And I haven't drawn what this function actually looks like. All I really know about it is that it's not defined at h is equal to 0. It's certainly not defined there because you're dividing through by 0. But what I do know about it is that its limit as you get closer and closer to 0 is this value p that I know is positive, not 0, not negative, positive. And now what I need to think about is the definition of this limit being equal to that, i.e. the epsilon delta definition, and see what I can work out from using that. So what I know from the fact that this limit exists is that for any epsilon I take, I can construct an epsilon interval around this value p, and there must exist a delta interval around h is equal to 0, such that all the points in that delta interval, apart from the center point itself, 0, are mapped into my epsilon interval. Now, I am going to take as my epsilon p divided by 2. And the reason I'm taking that is I want to make sure that my epsilon interval stays in the positive part of the real line. If I took, for example, epsilon is equal to 2p, then my epsilon interval would come right down here and would include part of the negative real line. I don't want to do that. I want to make sure that I can find a delta interval around h is equal to 0 where all of the values that this difference quotient is taking for those values in that delta interval are positive numbers. So that's why I'm going to take epsilon is equal to p over 2, and I've drawn on this p over 2 size interval around p here in white. And from the fact that this limit exists, I know that there must exist a delta interval around h is equal to 0, and I've drawn that here, so an interval from minus delta to delta, such that all the points inside there, apart from 0, are mapped into this interval here of radius p over 2. Now this should make you a bit worried, because remember the function that is represented here graphically is this function here, this difference quotient. Now, say you take some tiny little h inside this delta interval, then if you look at what this function is, it's requiring f prime at x0 plus that tiny little h. Now, my initial assumptions were that the first derivative exists at x0 and is equal to 0 there, and the second derivative exists at x0 and is greater than 0 there. I didn't make any other assumptions about whether the value of the derivative of this function even exists in these other points in the interval ab. I just took as my initial assumption that the derivative existed at x0 and the second derivative existed at x0 and was positive. So what if my first derivative doesn't actually exist at these points? Well, this is where the fact that the second derivative exists saves us. It means that it must exist, or that the first derivative must exist in some interval around x0, because otherwise how could this limit possibly exist? The fact that the second derivative exists means that this limit exists and is equal to this value p, and by definition of this limit existing, the epsilon delta definition is satisfied. So for this epsilon interval that I've got here of size p over 2, it must be the case that there exists a delta interval. Now this delta interval might have to be made absolutely tiny, but there must exist a delta interval such that for all these points inside this delta interval, this function here exists and is mapped into that epsilon interval, i.e. in particular, this function must exist, i.e. the first derivative at these values x0 plus h must exist, otherwise the function wouldn't even be defined. So the fact that this limit exists, the fact that the second derivative exists, means that we're saved. I don't need to put any more criteria on the existence for the first derivative. I just need the fact that the first derivative exists at x0 and is equal to 0, and the second derivative also exists there and is greater than 0. That saves me. It tells me that the first derivative of my function is forced to exist at more points than just x0, at least some tiny delta interval around x0. It must exist, otherwise this definition of the limit couldn't be satisfied that is needed for the second derivative to exist there. So overall, what I now know is that there must exist a delta interval centered around 0, such that every point in that interval apart from 0 itself, if you look at this function, this difference quotient, it exists and it is mapped into this epsilon interval around p, i.e. this difference quotient exists and it is a positive number. So let's now take that further. So firstly, I note that f prime at x0 by initial assumptions is equal to 0, so that part plays no role in here. So we can simplify this quotient here down to what I've got here. So I'm now concluding then that if I take any h inside this interval, negative delta to delta, apart from 0 itself, so I've subtracted off 0 here, then if I look at this quotient, f prime at x0 plus h divided by h, it is positive. That's what I'm now able to conclude, that this delta interval such that this is true must exist. Now I can take this further. I can split my interval into the two halves, the positive half, so from 0 to delta, and the negative half from negative delta to 0. Now if my h is in that positive half, then the thing that I'm dividing through by here is positive. Therefore, if I'm going to overall end up with something that is positive, I can conclude that the numerator must also be positive. So if h is in this positive half of the interval, I can conclude that f prime at x0 plus h is greater than 0. Whereas if I'm in the negative half of the interval, so if h is in negative delta to 0, then I'm dividing through by a negative number here, so if I'm going to end up with something that is positive, the numerator must also be negative, so I can conclude that for h is in that part of the interval, the f prime of x0 plus h, where of course h is now a negative number, so you're really going backwards, must be less than 0, and this now is very powerful. So let's take this information now and integrate it with our intuitive picture here. So look at what I've got here. I am saying that this delta exists such that if you take an h in the positive part of that delta interval, then the value of the derivative at x0 plus h is greater than 0, and if you take an h in the negative part of that interval, then I know that the derivative at x0 plus that negative h is less than 0. Integrate that with the picture up here. I can put this delta interval now around x0 here, and I now know that if I go to one of these points in the positive part of that interval, which corresponds to x0 plus h, where h is a positive, is in the positive part of the delta interval, i.e. if I look at this interval x0 to x0 plus delta, that the value of the derivative of the function f exists there. One, I've already tried to justify that extensively earlier. It must exist there, and it must be greater than 0. And I also know that if I look at the left part of the interval, so x0 minus delta to x0, that again the derivative must exist everywhere in that interval, and it must be less than 0 everywhere in that interval. And then I know that it exists and is equal to 0 at x0, which is in the middle of these two. So that overall is what I've been able to conclude from the fact that the second derivative exists and is positive. I've been able to conclude that there must exist this delta interval around x0 where the first derivative of the function exists for all the points in that delta interval. And moreover, if you go to the positive part, or the right part of the interval, so x0 to x0 plus delta, the value of the derivative is strictly greater than 0, and if you go to the left part of the interval, x0 minus delta to x0, the value of the derivative is strictly less than 0, and then we know it's 0 at the centre piece, x0 is equal to 0. So that's what we've got from this information, that bit of information here. So now what I'm going to do is I'm going to use this information to show that x0 is a minimum for the function over this delta interval from x0 minus delta to x0 plus delta. So this interval is actually going to be the interval that is needed in the definition for local minimum. How am I going to do this? I'm going to use the mean value theorem. So I'm going to start by going to the right part of the interval here and showing that any point in that right part of the interval is mapped onto something that is greater than what x0 is mapped onto, and then we'll go to the left part of the interval and show that anything in that left part of the interval is also mapped onto something that is greater than what x0 is mapped onto, and hence we'll have shown that the function has its minimum for that interval at x0. So starting with the right part then, so if I take an x that's in this right part of the interval, so from x0 to x0 plus delta, I'm now going to apply the mean value theorem for our initial function f from x0 to x, so over this interval here. So I need to verify that the conditions of the mean value theorem hold true. So I need to know that the function f is continuous over that closed interval and differentiable over the open interval. So I know in fact that it's differentiable everywhere on the interval from x0 minus delta to x0 plus delta. X is within that interval and so is x0. So we know differentiability implies continuity, so I can therefore conclude that the function is continuous at every point in this closed interval x0 to x, because every point in there is contained within the interval x0 minus delta to x0 plus delta. I also therefore know that it's differentiable everywhere from on the open interval x0 to x, again because that's contained in the interval from x0 minus delta to x0 plus delta, where we know that the function is differentiable. So the conditions for the mean value theorem to apply do hold true. So now the mean value theorem says that if I look at what the difference quotient from x0 to x is, that there must exist some value in between x0 and x where the derivative is equal to the value of that difference quotient. So the difference quotient is going to be f of x minus f of x0 divided by x minus x0. So this I can conclude must equal the value of the derivative at the function for some c between x0 and x. But that c must be inside this interval x0 to x0 plus delta, because x is within, is less than x0 plus delta, it's inside that right interval. And I know that the value of the derivative there is always greater than 0. So what I can conclude is that this difference quotient must also be greater than 0 because the only options for what it's equal to are all greater than 0. Now, because we're looking at the right interval at the moment, x is greater than x0, so this denominator is positive. Therefore, if we're going to come out from this quotient as a positive value, that means the numerator must also be greater than 0. So I can conclude that f of x minus f of x0 is greater than 0, and therefore just rearranging that, I can conclude that f of x is strictly greater than f of x0. So if you go to any of those x in the right part of this interval here and ask what is the value of the function there, it must be strictly greater than what the value of the function is at x0. So that's the right half of the interval done. Now I just need to go to the left half. So now, same tactic for the left side of this interval. So on that left side of the interval, remember, we know that the derivative is always less than 0, so we're going to be able to use the same tactic with the mean value theorem to infer something about the value of the function in this left half of the interval. So take some point x in the left part of the interval, so from x0 minus delta to x0, and we're going to apply the mean value theorem going from x to x0 this time, because we need to be going in the positive direction. So previously, when x0 was less than x, we were doing it from x0 to x, but this time we're going to be doing it from x to x0. Again, we can apply the mean value theorem because the function is going to be continuous everywhere over that closed interval and differentiable everywhere over that open interval for the same justification as we had previously, i.e. that we know it's differentiable everywhere on the interval from x0 minus delta to x0 plus delta, and hence it's continuous everywhere on that interval, and this interval is contained within that interval. So now, applying the mean value theorem then, the difference quotient from x to x0 is going to be f of x0 minus f of x divided by x minus x0, and we know that this will equal the derivative of the function at some c that's properly in between these two, but that c is therefore going to be inside this interval here, which we know is well, the derivative for every point in that interval is going to be less than 0, hence we can conclude that this must be less than 0. Now, looking at the denominator, x is greater than x0, so this is positive, so the only way that this overall is going to end up negative is if the numerator is negative, so we can hence conclude that f of x0 minus f of x is less than 0, and then just rearranging that, we get that f of x must therefore be greater than f of x0, and that's for any point x in the left part of this interval. So I've now proven that if you take any point x in the right part of the interval, that the value that it's mapped onto is greater than f of x0, and I've also proven that if you take any x in the left part of the interval, the value it's mapped onto is also greater than f of x0. Hence, the function has a minimum over that delta interval from x0 minus delta to x0 plus delta at x0. Hence, we found the interval over which the value of the function at x0 is a local minimum. So we've therefore proven this first part, that if you have a stationary point where the second derivative is greater than 0 at that stationary point, that you can conclude that that stationary point is a local minimum. We'll have a break here, and in the next part we'll go over the proof for this part, which is exactly the same, just with a few big but simple tweaks, but it will help us revise the argument that we've just gone through.